Hi, and welcome back to the Implementing and Administering Cisco Solutions, the CCNA 200-301 video series course by EC Council. My name is Glenn Singh. In this video, we are going to discuss the need for the spanning tree protocol. So let's dive on in. So you may be wondering what exactly is spanning tree, or what is STP, the spanning tree protocol. To put simply, the spanning tree protocol is actually designed to prevent layer 2 loops on a network. Most importantly, it is defined by IEEE 802.1d, which is the official standard for preventing layer 2 loops. So far, we are accustomed where we have multiple switches that are interconnected with each other on a network to provide redundancy. Being a network engineer, redundancy is very important. However, redundancy can also lead to bad things happening, such as creating loops and even generating broadcast storms on a network. So we want to keep redundancy, but we want to also prevent loops and broadcast storms. So how can we do this? This is where spanning tree, or STP, comes in to help us. With spanning tree, it creates a single active logical path between a source and destination on a switch network. Let's take a look at this diagram. Currently, we have redundancy between the switches. So, imagine PC1 wants to send data to the server. Well, PC1 will send a message to switch 1. Switch 1 has multiple paths. Now let's imagine that there's no spanning tree or any sort of loop prevention mechanism operating on this network. Switch 1 will forward the data up to trunk 2 and also forward the data as in a copy to trunk 1. The message that is on trunk 2 will come across on this side, while the message that is on trunk 1 will go to switch 2, then switch 2 will forward it to switch 3 and it will send an additional copy to the server. So therefore, the server receives duplication of this one message that was sent. Now imagine that the server has to respond. Since the server receives 2 messages, the server will respond 2 times. Once these 2 messages enter switch 3 will send the 2 messages down here and send 2 across here as well, which will be received by switch 2. The messages on trunk 2 will be delivered to switch 1, which are these 2 messages, together with the messages from trunk 3, will be received on switch 2 and be sent down to trunk 1. Therefore, these 2 messages across here will come across to switch 1. Therefore, PC1 will receive a total of 4 responses. This here is what we call duplication. This is one of the possible problems that can exist on a network. What if our network, as in our network devices, contain IP addresses? So let's say on this network, they belong to the 192.168.0.0/24 network. Let's say PC1 has an IP address of .10, PC2 has an IP address of .20, and the server, let's give the server .30. Okay, so this means that if PC1 wants to send a message to the server, PC1 knows the IP address and also knows the destination MAC address. So let's imagine that there's no loop prevention mechanism on the network. PC1 wants to send a message to the server. The message is sent from PC1 to switch 1. But while the message, as in this message, is in transit to switch 1, let's say the server happened to go down and it's no longer available. Well, switch 1 will forward a message to switch 3. Switch 3 will realize, hey, the server is not available, and therefore switch 3 will do the most typical thing once it receives a frame that it does not know where the destination is. A switch that receives a frame that does not know where the destination is will simply broadcast that frame out of all ports except the port the frame originated on. So this means that switch 3 will broadcast it out of this port. Switch 2 will receive the message and have no idea where the server is located, as in CCC. Switch 2 will broadcast it out of all ports. The message will come back down to switch 1. it will be broadcast, and this here will be a never-ending cycle. In other words, it's what we call a layer 2 loop that can exist on a network. So you're probably wondering, but wouldn't the message like fade away eventually? The thing about a frame, and we are talking about frames because all these are switches, frames do not have something called a TTL value, a time to live value. Only packets contain TTL values. So what is the purpose of a TTL? Well, every time your device sends a message to another device along a network, as long as they are layer 3 devices, let's say routers, every time the packet passes a router decreases the TTL value by 1. So therefore, if the packet is never delivered, whether it is on the internet or on a network, once a TTL value on a packet reaches 0, the router, to change that value to 0, simply discards the packet. This means that eventually a packet may be circulating within a loop, but eventually the TTL value will decrease to 0 and the packet will be discarded automatically. However, with a frame, there's no TTL value, so which means that all these messages keep on circulating over and over and regenerating, therefore creating a layer 2 loop within a switch network, and eventually it will generate a broadcast storm and congest the network. In this diagram, we have the Cisco 3-tier hierarchical structure: the core, the distribution, and the access. Imagine PC1 wants to send a message to, let's say, PCD. PC1, well, we said D, it's actually PC4. So imagine without spanning tree, PC1 sends a message to this switch, let's call this A1 for access switch 1. Well, without spanning tree, A1 will send it to the distribution switch 1, send it to distribution switch 2. Each of these switches, distribution switch 1 will forward it to all possible available paths. And as you can imagine, eventually all these switches will be looping the messages over and over and over, providing that PC4 is not available. But whether PC4 is available or not, guess what? Because these other switches are already regenerating the traffic, for some time the network will experience some congestion. But if we have, let's say, spanning tree implemented, well then, a possible path might be like this. It go to A1, A1 might send to this distribution switch, let's call this D1, D1 might forward it directly to, let's say, A4. And A4 will forward a message to the destination device. As you can see, this is one active path. So what exactly does spanning tree do? Spanning tree will ensure that there is only one active path on a network between a source and a destination. Furthermore, spanning tree will detect any sort of redundant paths or any additional redundant paths and place those links in a logically blocked state. Spanning tree does not shut down an interface, but what it will do is logically block that path or block that interface within the software itself. So let's say that this interface here is currently blocked by spanning tree. Therefore, any messages between PCA to PCD will have to take this highlighted path between switch A1 to D1 to A4 and then to the destination, which is PCD. So how does spanning tree able to detect, let's say, any redundant paths or available paths on a network? To put simply, on a Cisco switch, each Cisco switch automatically exchanges a very special type of frame. This frame is called a Bridge Protocol Data Unit, a BPDU. These BPDUs are exchanged every 2 seconds between switches. So therefore, if a switch does not receive a BPDU within a certain interval, a neighbor switch may consider a path to be down on the network. A BPDU is made up of 3 main elements. One of the elements is called the bridge ID. Each switch has a default priority value. and the default priority value is 32,768. This value can simply be modified as in increments or decrements of values of 4096. The lower the priority value simply means more likely that switch will become something called the root bridge. The root bridge simply tells all other switches which paths to open, which paths to block, and also the root bridge functions as a central reference point for all traffic within the VLAN itself. Additionally, within the BPDU, you can find something called the Extended System ID. For each VLAN to exist on a network, there is a separate spanning tree instance for that particular VLAN. So by default, since VLAN 1 exists on all switches, spanning tree is running for VLAN 1. Now, the Extended System ID is used to identify the VLAN ID for that specific spanning tree instance. So therefore, all switches that are running spanning tree for, let's say, VLAN number 1, the Extended System ID within their PPDUs will be 1. The third element is called the MAC address. This is the MAC address of the switch that one switch used to communicate with another device on the network. In this diagram, shows the contents of a BPDU of a switch. As you can see, there's a bridge priority value, there's the Extended System ID, and there's also the MAC address of the switch. To get an idea of the find or where do you find the MAC address of a switch, let's quickly take a look at one of our labs. So let's say that I want to get a MAC address of any of these switches. I can simply click on one or access the command line interface, and I could use the show version command like so. So I have executed the show version command in privilege mode, and looking here, the base Ethernet MAC address, this here is a MAC address for this switch. So therefore the BPDU will contain this MAC address value. Previously, we mentioned the root bridge. So what exactly is the root bridge? Why do we need a root bridge? Well, firstly, the root bridge is determined as a switch with the lowest priority value. If all the switches has the same priority value for a particular VLAN, then the switch with the lowest MAC address is elected to become the root bridge. As mentioned, the root bridge tells all other switches which paths to open and which paths to close. Therefore, the root bridge controls how the whole spanning tree instance works for that particular VLAN. Furthermore, the root bridge serves as a central reference point for all traffic for that particular VLAN as well. The thing about the root bridge is for each VLAN to exist on a network, there's a root bridge for each VLAN. So this means if there are 3 VLANs, there are 3 root bridges on that network. Once a root bridge has been elected on the VLAN, all other switches will simply point towards that particular root bridge. As again, simply because the root bridge is a central reference point for all traffic for that VLAN. Each switch will contain the root ID of the root bridge within their own spanning tree instance. As good practice, it is recommended to create a secondary root bridge. Of course, having a secondary root bridge is redundant simply because if the primary root bridge fails, you know which switch will become the root bridge. Thus, creating a secondary root bridge can be created by simply assigning a priority value of 1 increment of 4096 higher than the priority value of the root bridge. This would simply create the effect if the root bridge should fail, the secondary root bridge will step in and take up the role of the new root bridge on the network. An important thing to know as a network engineer is the various port roles when using spanning tree. In spanning tree, there are three main types of port rules. There's the root ports, the designated ports, the alternate or backup ports. So what exactly is the root ports? The root ports are ports that are closest to the root bridge. Please keep in mind that these ports are not on the root bridge, but closest. Designated ports are simply non-root ports which are still permitted to forward traffic. While the alternate or backup ports, these ports are the ports that spanning tree logically place in a blocking state simply to prevent any sort of layer 2 loop on any redundant paths on your physical network. Within spanning tree, there's also port states. And of course, there are four main port states. There's blocking, there's listening, learning, forwarding. In the blocking state, the user data is not passed on to the network. However, BPDUs are still received on this port. So have you ever noticed that whenever you boot up a Cisco switch, it does not immediately forward your data between one device to another device? Simply because in spanning tree, it has to go through all these port states from blocking to a forwarding state. So with blocking, it does not forward your traffic, but it still is able to receive BPDUs on this interface. The other state is listening. In the listening state, the switch processes all the BPDUs, but neither forward any user traffic nor frames onto the network itself. The third state is learning. In the learning state, BPDUs are processed and the switch also learns MAC addresses, populates its CAM table, but it does not forward frames as yet. The fourth state is forwarding. This is the normal operational or the normal operating state of a Cisco switch interface. In the forwarding state, it is able to send and receive users' data and still process BPDUs. In this snippet, we are checking the spanning tree instance by simply using the show spanning tree command. We can see the instance is providing us the information for VLAN 1. We can see the root ID information here. We can see the root ID, as in the root bridge priority value, the root bridge's MAC address, the cost to reach the root bridge, the port, even the hello timer. The hello timer simply validates the default BPDU timers on switches, which is 2 seconds. On this local switch, which is C1, we have C1's bridge ID information. C1's bridge ID is 32,769. So you're probably wondering, isn't that the default priority value is 32,768? And yes, this is the default priority value. So we need to be a bit careful when observing an output like this. Simply because the priority value is this value here within the brackets. And remember, the bridge ID is the priority value plus the extended system ID plus the MAC address. So looking carefully here, we have the extended system ID, which is 1. So therefore 32,768 plus 1 will give us the bridge ID value of 32,769. The MAC address is given separate on the output. This MAC address here, which is 0003.E425.A0AA, belongs to this local switch, which is C1. Looking further, we can see the interfaces of this switch right now. We can see the roles of each of these ports. We have designated ports, we have root ports, we have alternate ports. We can also see the status. We have ports in forwarding state. We even have a blocking port as well. Understanding the output thoroughly in this diagram is very important. Don't worry. In a later video, we'll take a look at configuring and readjusting spanning tree. As a network engineer or a network administrator, you may be tasked to find or discover the root bridge. So why is such a task important? Sometimes when you get hired in a company, the network is already built, and it is your job to probably optimize or reconfigure and improve the network itself. And one of the first things you need to do is to be able to identify the root bridge. Here, I've listed 4 essential points that I use as my personal guidelines to discover the root bridge. So the first thing I want to do is identify the root bridge. Once I identify the root bridge, I would then identify the root ports. After identifying the root ports, I will then attempt to identify the designated ports, and then lastly identify the alternate or the blocking ports. So let's take a look at a simple exercise on how we can identify the root bridge and also label all of our ports as well. So now let's take a look at identifying the root bridge and labeling our ports. Firstly, we need to observe which switch has the lowest bridge ID. Well, to be more specific, which switch has the lowest priority value. If you recall, the switch with the lowest priority value will take precedence in becoming the root bridge. And as we can see here, switch 2 has a priority value of 24,577. So then therefore, switch 2 will become the root bridge. Now that switch 2 is the root bridge, let's move on to the next step. The next step is we need to identify the root ports. Remember, the root ports are the ports closest to the root bridge. The root ports are never on the root bridge. So to put simply, switch 1's fast Ethernet 01 will be a root port because it exists closest to the root bridge. Also, switch 4 fast Ethernet 04 is also a root port because it is simply closest to the root bridge. Right now we are at a slight dilemma because we need to determine which of these ports, whether it's this one, this one, this one, or even this one, will be the next root port. Remember, we cannot have root ports at both ends. Simply because if we have a root port, the other end will be a designated port. Therefore, let's imagine that we put a root port here, one here. Therefore, here will be designated, here will be designated. And there will be no sort of loop prevention mechanism activated. But we have spanning tree, so therefore, one side needs to be a root port while the other side is restricted or blocked. So how can we determine which of these interfaces will be the root port? Well, we already set the root ports on switch 1 and switch 4. So now we need to determine which ports on switch 3 will be the root port. Will it be fast Ethernet 02 or fast Ethernet 03? That's an important question. Now, we can look at the possible paths to the root bridge from switch 3. Switch 3 can take this direction or it could take this direction. But which one will it choose? To make this decision, we can look at switch 1's priority value and switch 4's priority value. The switch with a lower priority value will be the preferred path. But look closely, we can see that switch 1 priority value is the same as switch 4. So priority values are the same. Now what can we use as the other deciding factor since both priorities are equal value? We could look at the MAC addresses. Each switch has a unique MAC address. Currently, we can see switch 1's MAC address is lower than switch 4's MAC address. Therefore, switch 3 will choose this path to reach to the root bridge and not via switch 4. So what does this mean? This simply means that fast Ethernet 02 on switch 3 will be a root port. And there we go, we have now labeled out all our root port. If you recall, the root ports always point to the root bridge. And because switch 1 has a lower MAC address, switch 1 will be the preferred path for any data that is originating or passing through switch 3 to go to the root bridge. Now that we have identified the root bridge and we identified the root ports, the third step is let us identify the designated ports. First of all, one key tip is all ports on the root bridges, or all ports on the root bridge, are designated ports. So you can quickly label these as designated ports. Furthermore, once we have a root port on one side of a link, the other side is also a designated port as well. That's another key thing to to pay attention to. Right now, we have to label these two ports here. Fast CCNA 03 on switch 3, fast CCNA 03 on switch 4. Which of these ports will be designated and which of these ports will be blocking? Both of these interfaces cannot be forwarding, because if both of these interfaces are forwarding, this means we will experience a layer 2 loop, simply because root ports forward traffic, designated ports forward traffic. So we need to figure out which one of these ports will be a designated port and which port will be an alternate port. To help us decide, we could take a look at the priority value between switch 3 and switch 4. Well, the thing is, both priorities are the same. So if both priorities are the same, then the other deciding factor will be the MAC addresses. We can see that switch 3 MAC address is lower than that of switch 4. So it is always a device with a lower priority value, or the lower MAC address will take precedence in becoming the preferred port for forwarding traffic. So this means switch 3 interface will be designated, while switch 4 will be the alternate, and this port will be in a logically blocked state, simply by spanning tree. Therefore, if there's any PC connected to, let's say, switch 3, let's say we have PC1 and PC2, if PC1 needs to send data, let's say to the root bridge, the traffic will take this path. Therefore, right now on this entire network, we have one logical path throughout the network. And this here is an example on how to quickly identify the root bridge and also identify the root ports. In spanning tree, there are different modes. Spanning tree, as we know, is defined by IEEE 822.1d, and this here is an open source standard. The thing about spanning tree, it's very slow on convergence. And this can be an issue, especially if you have a very large network that requires high availability. Cisco took the open source version of spanning tree and made their own proprietary version, which is called Per VLAN Spanning Tree Plus, or better known as PVST Plus. Cisco also took another variation of spanning tree, which is known as Rapid Spanning Tree, which provides faster convergence, and made their own version, which is called Rapid PVST Plus. With PVST Plus, the Cisco proprietary version of spanning tree supports the following rules for their interfaces. There's blocking, listening, learning, and forwarding. Please ensure that you remember these port states simply because you are required to know it for the official exam. In this video, we discovered how layer 2 loops can destroy a network. We also took a look at discussing and understanding the functions of spanning tree protocol, and we also explore some features of PVST+. In the next video, we will be taking a look at actually configuring PVST+ on a Cisco network. I hope this video has been informative for you, and I hope to see you in the next one.